Hello, and welcome to the Sequences and Series video. This topic is based on number patterns and sequences which we've covered in previous years and builds a little bit onto it with a few new aspects. For this topic, first we'll be covering sequences, and under it we'll first revise a bit on arithmetic as well as quadratic sequences. Then we'll cover geometric sequences. Next we'll look at the series section, which will include sigma notation, then finite arithmetic, followed by geometric series. And lastly, we'll look at infinite series. Let's begin. Arithmetic sequences. These are defined as sequences where you can get the next term in a sequence by adding a fixed number to the current term, which is defined as the common difference, d. For example, we can look at the following sequence. Just by seeing it, some trends should become apparent. Each subsequent term increases by 2, meaning that you added 2 to each term to get the next one, implying a common difference of 2. Key thing to note is that it's called a common difference, so it has to be the same for every pair of terms in the sequence. If at any point it changes, then it means it isn't a common difference. So for this sequence, we can check whether it stays the same by calculating the difference for various pairs. Let's try it for the first and second term, where the difference is second term minus first term. You should be familiar with this notation, by the way, where you have a capital T followed by a number after it. The T stands for term, and the number represents whichever term you're talking about in this particular case. So for first term, you have a T1, which would be this guy, and for second term, it would be T2, which would be this value, and so on and so forth. Anyway, back to the example. You try it for the first and second term, where you have 0 minus minus 2, which gives you a value of 2. Meaning the first pair we tried has told us that the common difference is 2. But that's just one of the pairs. We have to try it for a few more to establish that it is actually common. So we can try it for the second and third term this time, where it's T3 minus T2, which gives you a value of 2 again. So you got the common difference as 2 for two different pairs. So we're starting to get a bit confident that it actually is a common difference. But as they say, third time's a charm. So we can try the third time with, say, the fourth and fifth term, which again gives us a value of 2. The point of this example was to demonstrate that the common difference, in this case 2, needs to stay the same for it to be considered an arithmetic sequence. So if the sequence was instead the following, where for the first few terms you have a difference of 2 for the first 3 terms, then the difference suddenly changes to something else, such as 3 in this case. Then it can't be considered a common difference, and this wouldn't count as an arithmetic sequence. We can look at one more example. I use this example mainly to demonstrate that the common difference doesn't have to only be a positive difference. It can be a negative difference as well. Let's calculate it for various terms. So for the first and second term, meaning T2 minus T1, it is minus 0.5 minus 1, giving us a value of negative 1.5. And for the second and third term, we get negative 2 minus negative 0.5, giving us negative 1.5 again. Then last, we can check for the fourth and fifth terms, where it's negative 5 minus negative 3.5, which gives us negative 1.5 as a difference again. That confirms this is an arithmetic sequence with a common difference d of negative 1.5. Next, we'll look at how to determine the general term of an arithmetic sequence. First, some notation which you should be familiar with. A represents the very first term in the sequence. So looking at the two examples we just looked at, for the first one, A would be negative 2. For the second one, A would be 1. I'll just add the common differences we calculated above to the side over here. Then the second term to become familiar with is n, and the nth term. N represents the position of a number in a sequence. So using the above two examples, For the first term, n is equal to 1. For the second term, n is equal to 2. And for the third term, n is equal to 3. And so on and so forth. Now we know what n represents, so that leaves you to ask, what is the nth term? By the nth term of a sequence, we mean a formula that allows us to find the value of any term in the sequence, provided we know its position, meaning its n value. For example, with this first sequence, say I wanted to find the value of the fifth term in the sequence. If I knew the nth term formula, I could just use the n value, meaning 5 in this case, to find its value. So as long as I know the first value in the sequence, meaning a, and the common difference d between each term, which we know is 2 from before, I wouldn't need to write out the whole sequence and be like, okay, minus 2 plus 2 is 0, 0 plus 2 is 2, 2 plus 2 is 4, and yada yada, till I reach the fifth value. This would take quite a lot of time. Okay, fine. If it was just the fifth value, then it wouldn't take so long. But in the exams, for example, the question will ask you for like the 90th value in the sequence, in which case it would take forever to determine it. But if you have the nth term formula, you could do this very quickly. The following is the general nth term formula. Another useful visual trick to help you grasp this idea is to write out a row for n values above a sequence every time you're given one, like the following for the first sequence. It's pretty simple, just starting with 1 and going upwards, one at a time. It may seem like unnecessary extra efforts, but if you're still a bit foggy with the whole nth term concepts, it's a useful visual tool because it makes it a little easier to see. And after you've done it many times, just from memory, you can sort of see it floating above and won't really need to draw it out. Anyway, so let's apply this formula to see how it works. We know the values of a and d from before as -2 and 2. Then we have the equation as a plus n minus 1 d. So just substitute the a and d values into this, which gives you. And when you break this down, you finally arrive at a formula of 2n minus 4, meaning our nth term for the sequence is 2n minus 4. And we can use this formula to calculate the value of any term in the sequence as long as we know its position. Let's try it out. For the first term, n is 1. And when we sub this into the above equation, we get a value of -2, which is correct. For the second term, n is equal to 2. When we sub this in, we get a value of 0, which again is correct. Then, for the third term, n is equal to 3, and for it we get a value of 2, which again is correct. You can try it by yourself for the other terms in the sequence, but you should see that you'll keep getting the correct values. Now let's try it for the other sequence we looked at. Sorry, I had to make it a little smaller than it was up here. So it could fit into the table. And these are the a and d values we got. So I'll leave it to you to work out the nth term equation for this sequence so you can get some practice. You can pause here to work on it and come back to the video where I'll give the final nth term equation. So this is the final nth term equation you get, which is 2.5 minus 1.5n. If you feel comfortable with arithmetic sequences, we can now move on to quadratic sequences. Quadratic sequence is defined as a sequence of numbers in which the second difference between consecutive terms is constant. For example, the following sequence. If, like before, you calculate the difference between each term, you'll notice that these differences aren't the same the way they were for the arithmetic sequences. This set of numbers is known as the first difference. Then, if you calculate the differences between these numbers, you get what is known as a second difference. Now you see a constant value of 4 in this case. Since this sequence has a constant second difference, it can be characterized as a quadratic sequence. Here's another example. The first difference values for it are, all of which are different again. Then when you calculate the second differences, you get the following. A constant second difference of 6 this time. So this also qualifies as a quadratic sequence. Next, similarly to how you did for the arithmetic sequence, you need to know how to find the nth term of the sequence. Because as mentioned earlier, you can't keep writing out the whole entire sequence if you want to find out the value of some term somewhere down the line, which is where the nth term equation comes in handy. For quadratic sequences, the nth term equation is a quadratic equation. This time, the main effort is in finding the values of the terms a, b, and c. First thing to keep in mind is that this time a doesn't refer to the first term, but instead it's actually something different. The way it works is you first determine what equations you'd get in terms of a, b, and c for the first three terms, meaning for the cases where the n values are 1, 2, and 3. So you just sub these n values into this equation. We'll go at it one term at a time. For the first term, n is equal to 1. If you sub this into this equation, you get a plus b plus c. Then you do the same for the second and third term to give you these two equations. So for n is equal to 2, you get 4a plus 2b plus c, and for n equals 3, you get 9a plus 3b plus c. Next, you write them in a similar form like above, this form. So start by writing the three terms like this. Then you need to find their differences. So you say t2 minus t1, giving you the difference as 3a plus b. And when you subtract t2 from t3, you get 5a plus b. So you now have the equations representing the first difference. Then you subtract this term from this term to get your second difference, which gives you. Now you can use this information to determine the nth term of any quadratic sequence as long as you know the first three terms in it. The main points to take away from this are three equations in particular. First, you should know that second difference equals to 2a, meaning that a equals to second difference divided by 2. Next, you should know that the first difference is equal to 3a plus b. And lastly, you should know that the first term is equal to a plus b plus c. It probably seems a little hectic and abstract now, just seeing all these different letters, but it will become much clearer once we have some numbers. Let's look at a sequence from earlier on. This one. There's the sequence. First calculate all the first differences and you get 0, 4, 8, and 16. So none of them are equal. So you continue and calculate the second difference and you get 4 for all of them, which tells you that this is indeed a quadratic sequence. So from the first equation above, we know that the second difference is equal to 2a. And for this sequence, second difference is equal to 4. Therefore, a equals to 2. Next, we know that the first difference is equal to 3a plus b. So for this quadratic sequence, that means 3a plus b is equal to 0. And we already know that a is 2 from this calculation. So when we sub in this a value into this equation and rearrange for b, we get b as negative 6. And lastly, we know that the first term is equal to a plus b plus c. In this case, the first term is equal to 1. Therefore, a plus b plus c equals 1. And we already know the values for a and b. So when we sub this in and rearrange for c, we find c to equal 5. Putting this all together, we get tn equals to an squared, so 2n squared, plus bn, so minus 6n, plus c, so plus 5. So finally, the nth term formula for this sequence is 2n squared minus 6n plus 5. Now the last thing to do is to test whether this equation actually works and gives us the correct values for various terms in the sequence. Let's try it out for the first three terms, meaning for n equals to 1, 2, and 3. For the first term, n equals to 1. And when we substitute this n value into the equation above, we get a value of 1. And when we look at the first term's value above, it is equal to 1. So it's correct. Next, for the second term, we get again a value of 1. And looking back at the sequence, we can see that the second term is indeed 1. Lastly, we'll look at the third term, which gives us a value of 5, which is the same as the third term in the sequence. So that confirms that the equation is correct. And that is how you determine the nth term for a quadratic sequence. So far, this was all a revision of things you've covered previously, but it is worth going over properly because you'll still be asked questions related to arithmetic and quadratic sequences in your exam. Moving on to new material now, let's look at geometric sequences. A geometric sequence is a sequence of numbers in which each new term is calculated by multiplying the previous one by a constant value known as a constant ratio, r. R is calculated by dividing each term by the term directly before it, which is the same as saying Tn over Tn minus 1. Some examples of geometric sequences are: on first glance, you may notice some pattern, a sort of doubling of each subsequent value, but let's actually calculate it. Let's try for the first two terms. We focus on the second term, meaning n equals 2. Then based on this equation, Tn would be T2 and Tn minus 1 would be T1. Then we substitute the corresponding values for the two terms, giving us 4 over 2, which gives us the constant ratio value as 2. This value is called the constant ratio, meaning the value has to be the same for every pair of terms. Therefore, let's try again with the second and third terms, meaning n would equal 3, so Tn over Tn minus 1 is T3 over T2. And when we sub in the values, we get the ratio as 2 again. For a third attempt, let's look at the last two terms in the sequence, so 32 and 64. So n would be 6 in this case, since the second value in the pair we're looking at is the sixth term in the sequence. Keep in mind that whenever using this equation, the value of n always refers to the position of the second term in the pair you are focusing on, which would be 6 in this case, since 64 is in the sixth position of the sequence. So we get T6 over T5, and after subbing in the values, we get constant ratio as 2 again. Let's look at another sequence. This is the sequence. This sequence looks a little more hectic, but we just follow the exact same procedure to find out the common ratio. Just for fun, let's start at the end this time. So that would be the third and fourth terms. The value of n would correspond to the second term in the pair, meaning that n would equal 4. So that gives us T4 over T3, which is 0.007 over 0.07, which gives us the common ratio value as 0.1. Next, we tried for the second and third terms, so T3 over T2. We substitute in the values and get the ratio as 0.1 again. Last, we try out the first and second term. We substitute the values, get the ratio again as 0.1. You should now have a pretty decent feel for how geometric sequences work and what the constant ratio represents. Next, we need to learn how to determine the general term for the geometric sequence, or rather, the nth term. As earlier mentioned, the general nth term formula is where a is the first term in the sequence and r is the constant ratio. Let's apply this equation to two sequences we already looked at to see it in action. We know from earlier that r equals to 2 for this sequence, and a is the first term, so that would be 2 in this case. Then we're pretty much done. We just substitute these values into the equation above and get the nth term formula as, this formula has a lot of 2's in it, but since we know how exponents work, we can simplify this, which gives us the equation as, so our nth term equation is 2 to the power of n. To confirm it's correct, we can use it to see if we get some of the terms in the sequence. For the first term, n equals to 1. So we say 2 to the power of 1, which gives us a value of 2, which is the same as the first term in the sequence. Next, let's try it out with the third term in the sequence, so where n equals to 3. So we have 2 to the power of 3, which is 8. This is the same value as the third term in the sequence. You can test it out by yourself with these other values, but it looks like we have the correct formula. Then let's try this out with the other sequence we looked at. That's the other sequence. For this sequence, we found the constant ratio to have a value of 0.1, and we can see that the first term is 7. Therefore, our nth term equation would be 7 times 0.1 to the power n minus 1. We can't really further simplify it like we did for the other equation, so therefore this is our final nth term equation. Let's test it out using the first and last terms. For first term, n is equal to 1, which gives us 7 times 0.1 to the power 1 minus 1, which is just 7 times 0.1 to the power of 0, which just equals 7, which is the same as the first value in the sequence. Then for the last term, this sequence has 4 values in total, so for the last term, n is equal to 4. Then we substitute everything in and we get 7 times 0.001, which is just 0.007, which is the same as the last term in the sequence. So we know our nth term equation is correct. And with that, we've completed the sequences section. Sequences forms the foundation for the series section, which comes next. So don't go through the series section until you're completely comfortable with the material for sequences. I would go through some past exam level questions at this point, but exam questions are usually a combination of sequences and series material. So it could be something like, for example, question 2 would be the sequences and series question. Then you'd have parts 2.1 and 2.2 would be on sequences. Then parts 2.3 and 2.4 would be on series. So I think let's rather cover series as well. Then we can look at the exam type questions and answer them in the entirety. At this point, I'll just summarize the material related to sequences that we covered in this video. To summarize what we covered in this video, first we looked at arithmetic sequences. The main principle in it was that there's a common difference d between every two consecutive terms, which you can find by subtracting the first term from the second, or in equation form it can be written as d equals to tn minus 1. Then the general formula, or otherwise known as the nth term equation for an arithmetic sequence, is Tn equals to a plus n minus 1 d, where a represents the first term in the sequence. Next, we looked at quadratic sequences. The defining principle for these is that they have a common second difference between every 3 consecutive terms, and the nth term equation is Tn equals to an squared plus bn plus c, where a is half of the second difference between the terms. Then you find b using the equations you have for the first difference, and you determine c using the equation for the first term in the sequence. Next, we looked at geometric sequences. Their defining principle is that there's a constant ratio r between each pair of consecutive terms, or in equation form calculated using r equals to tn over tn minus 1. And finally, the nth term equation for geometric sequences is Tn equals to a times r to the power of n minus 1, where a is the first term in the sequence. And that's everything we covered in the sequences section. Now to move on to the series section.